Alright, so the red, the green, and the blue show different paths that a gas could be taken through. And I have an example over here on the right of what would be called state A. This would be point A in a cylinder where there's a piston that's keeping a gas contained. And right now the volume of that at point A is 30 meters cubed. That lines up with the axes that are given here because this volume is in meters cubed. And then the pressure is in pascals. So when we're at A, we've got 30 meters cubed. If we were to compress this gas, say, to point D, down here's a good picture of point D. Here, the volume would be only 10 meters cubed. Yeah, so when the piston is raised, that could represent state A, where we've got a large volume in the cylinder. And then when the piston is lowered, the gas is compressed to 1/3 of its volume. That could represent state D, for example. However, it could also represent state C, because state C is also at 10 meters cubed. So what's the difference between D and C? Well, while D is at low volume, D is also at low pressure. But C is low volume and high pressure. So how do you know it's high pressure? Because it's high up on the pressure axis. Now they say that the vertical axis, each mark there is worth 3 atmospheres. Okay, so we're actually not in pascals then. We'll change our units to ATM. So this is going to be 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. So if we're talking about state D, we're at 6 atmospheres of pressure. But if we're in state C, we're at 27 atmospheres of pressure. And visually, it would be hard to tell the difference, because the piston would still be lowered to the same setting here, or same position. And then you've got some particles. Now, since the gas is contained inside the cylinder, particles can't escape. So you have the same number of them inside state C as D. So let's call this one on the left state C, and over here is state D. And so they're both 10 meters cubed. That's their volume. But one of them has a higher pressure than the other. C has a high pressure, whereas D does not. So how can you show pressure in this diagram? One thing you could do is show that according to the formula PV equals nRT, they have the same volumes. This is constant for both C and D. They have the same N. N is the number of particles inside the cylinder. And R is actually what we call just a gas constant, which is going to be the same for all ideal gases. And so what this means is that if one of them has a high pressure, it must have a higher temperature as well. So let's write that this is going to be a high temperature. And this one must be at low temperature then. All right, now they want us to, if we wanted to show that, one thing we could do is attach arrows to the particles to show that their speeds are related to the temperature. So it must be that in this cylinder C here, the particles are really moving around rapidly. Whereas in D, you get the same number of particles, but they would just have short arrows, so they would have slow speeds. Okay, so slow speeds. This would be fast speeds. Okay, so what accounts for the difference? Like, why is it that in state C you could have a different temperature than state D? Well, you could have heat flow. You could have energy flow into or out of the cylinder. Anyway, in this problem, what they really want us to do is to find the work done along a path and calculate the area between the path curve and the horizontal volume axis. We want to know what is the work done on the gas in order to compress it from point A to point C. Okay, so the work can be found on the graph itself if we calculate the area finding the area under the A to C path. And it's not just the triangle, actually, to get the work done. It's going to be the whole thing, like all the way down to the volume axis. So we need that shape to be calculated. We need to find its area. It's going to be a trapezoid, or you could think of it as a rectangle plus a triangle. So let's see if we can calculate the different shapes here. We need the height of it. It's going to be 27 minus 6. And then we're going to need the height of this little rectangle piece, which looks like that's 6. So 27 minus 6 makes 21. And then you also need the base, which is this here, and that's 30 minus 10, which is 20. Yeah, so if we just do area of a triangle formula, it's going to be 1/2 base times height. So 1/2 of 20 times 21. But we want to think about the units. If we do 20 and 21, that's going to be meters cubed and atmospheres. But when we calculate work, we typically want joules. Okay, so if we want joules, we have to use the SI unit of pressure, which is not atmospheres, but pascals. So we won't use the 21. Well, we can, but we just want to convert it. So let me write in the units. Yeah, 20 meters cubed. Yeah, 21 atmospheres. But now we throw in a conversion to change atmospheres into pascals. And that's given in the problem right here, the conversion between them. It's saying 101,325 pascals is 1 atmosphere. That's atmospheric pressure. So with that in mind, we can now multiply to get the area of the triangle piece. I get 21 million joules. That is for the triangle. Now we also want to find the area of this rectangle down below. So the area of the rectangle will be just base times the height. So that's going to be 20 meters cubed. Okay, so 20 meters cubed times 6 atmospheres times 101,325 pascals per atmosphere. So the area of the rectangle is 12 million joules. All right. Now we just want to add those together, and that will give us the work that's done when you compress that gas along that path. The idea being that it takes more work to compress the thing when it's at high pressure than it does to compress it when it's at low pressure. Like, it's easy to compress a gas that's at low pressure. Much more difficult to compress it when it's highly pressurized. So I just want to add them two together. I get a total work done being 33,440,000 joules. Now, how do you know whether work is done by the gas or on the gas? Well, since we're going from high volume to low volume, that's always work done on the gas, because you're changing the gas's volume by pushing all the particles down and compressing it. So see, these particles will feel forces making them move in the direction that the piston is compressing them, and so they each have a force and a displacement here, and that's going to be the work done on them. It's going to be positive because the piston is pushing down and the particles actually will go down. So this would be an example of work being done on the gas. A gas can also do work, though, on the surroundings if it expands. Okay, if the gas is compressed along the path A, B, C, what is the work done on the gas? All right, this time we're going to take path A. We're going to go A to B, and then from B to C. So the path from A to B, it's called an that path A to B is an isovolumetric path. So what it does is there will be a changing pressure, but isovolumetric means that the volume remains constant. Along that path. We can see that the volume is 30 at the start, and the volume is still 30 at the end. So both of these have a V of 30 meters cubed. So when you don't change your volume, you would have no work done. We also see that the area underneath that segment would be nothing because it's just a line. There is no substantial area underneath it. But what is happening is the pressure is changing. So we're at low pressure down here at A, and then at B, we're going to high pressure. All right, so what could be an example of this? Let's say you have a tank where there's a certain position that the piston is at. And let's say that piston is just going to be held there and it's not going to move. And so it's containing some gas. So you got a bunch of particles here, and their volume is held fixed at 30. But if you want the pressure to change, there's one thing you could do, at least according to the ideal gas law, PV equals nRT. You hold volume constant. The piston here is locked in place, so it's not going to go up or down. Since it's containing a substance, and let's say that these walls are metal, and you just can't transfer material in and out, then the N number of moles would be called number of moles of gas is constant, and the volume is constant. This R, the gas constant, is by definition a constant. It's not going to change. So one way you can increase the pressure would be to introduce heat flow into your gas. So you could say apply a flame to this. Then we would have energy flowing in as heat, Q, and then the energy of those particles would increase. And that means that the temperature could increase. Now the particles are really moving a lot faster. They're hitting the container walls a lot more. So now you got higher pressure if you do that. Okay, so that is path AB. What about path BC? Now you want to retain a constant pressure. They would call that isobaric, an isobaric change. And in isobaric, the pressure remains constant. But the volume here is changing. Since the volume is changing, we assume that the piston is moving down. And we just need to find the work done from B to C by actually calculating the area underneath that segment BC. But it does extend all the way to the horizontal axis. This is the area that we want to get. And in fact, that's a formula for work. Work equals pressure times change in volume. It's similar to the work formula we had used before. We had force times displacement. We can also, derive this formula of pressure times delta V is also an expression of the work. And that's what we'd be calculating when we get that rectangular area here. Alright, so the pressure is a constant 27 atmospheres. we want to multiply that by the delta V. All right, now, if we do delta V being V final minus V initial, then what you're calculating is the work done by the gas. Because we're going to get a negative here. So that would not be the work done on the gas, because the work done on the gas is actually going to be positive. But the work done by the gas is the opposite, basically by Newton's third law. So now we can multiply, to change the atmospheres, we just want a conversion factor. I'll just do it down here. So we have 10 meters cubed at the end, 30 meters cubed initially. Change the atmospheres to pascals. And this will be the work done by the gas. So it comes out to a negative. Negative 54,720,000 joules. And so what is the meaning of the negative? Well, you got to figure that those particles, they're hitting the container walls from the inside of the container. They want to push the walls outward, and they want to push the piston upward. But the thing is, the piston doesn't go upward. Even though they're pushing against it, the piston ends up pushing them down. And so whenever you apply a force in one direction, but the object doesn't go in the direction that you're pushing, then you've done negative work. And so that's what's happening here with the gas particles, is they are doing negative work because they are being compressed. So instead of having energy flow out, energy would be flowing into the gas. Okay, now in this particular case, that energy does not result in a change in pressure. So what is happening there? The answer would come from the first law of thermodynamics. And what the first law says is that the change in the internal energy of a gas can equal a sum of the heat flow into the gas plus the work done on the gas. So what they're saying is if work gets done on the gas, it is possible for the internal energy of the gas to increase. But it could also be possible for heat to flow out of the gas instead. One subtle difference between what I put in the box here and what they're asking for is they're asking for the work done on the gas. But I had given the work done by the gas. And so we're going to always find that the work done by the gas is going to equal the opposite of the work done on the gas. That is by Newton's third law. So with that in mind, the work done on the gas will be positive 54,720,000 joules. Yeah, because the piston does go down in this situation. You're going from a high volume of 30 down to a low volume of 10. So that means the work is going to be done on the gas. Now, one way to look at a PV diagram and know that would be the case is if you're going to the left. If you're going to the left, then there's going to be what's called a compression. And whenever there's a compression, positive work is done on the gas, but negative work is done by the gas. So when I see that backwards arrow, I just always assume make this area a negative. It's going to be negative work done by the gas. If you instead go forward, that would be an expansion, and that would be positive work done by the gas. Okay, so now let's examine what would happen if we took path ADC. If you take path ADC, first you're going to undergo an isobaric compression, it's called. There, our gas is taken from 30 meters cubed down to 10. And when it comes to our pressure, it's not going to change. It's just going to stay 6. It's going to stay 6 atmospheres throughout. So work is going to be done during that transition. The work done will be given by the area under that segment there. As you can see, this is a much smaller area than we would have had going from B to C. When we went from B to C, we had to get all this area underneath it, so our height was 27. Down here, our height of our rectangle is only going to be 6. And then our delta V is going to be 20. So we just want to multiply those to get the work done. And just remembering that we are going to the left, this is a compression, so that means the work done by the gas is going to be negative. But if we want the work done on the gas, it would be positive. Okay, let's see what it is. Negative 12 million joules done by the gas and positive 12 million joules done on the gas. Okay, so that just means that if you've got the piston here, it starts off high and it is going to move downward. So piston moves downward to a new location. Okay, and then compresses this gas to a small volume. That would be positive work done on the gas. All right, now there can also be heat flow into or out of the gas as well, according to the first law of thermodynamics. So the first law says change in internal energy equals Q into the gas plus the work done on the gas. So we know that the work done on the gas is positive. It's 12 million joules. Now, is it the case that all of that energy goes into internal energy for the gas? Or is it the case that all of the energy leaves the cylinder as heat? Now, we haven't talked about how to determine that yet. But one thing we would be able to tell is that D is at a lower temperature than A. Now, how do I know that? Because in these PV diagrams, there are things called isotherms. And what isotherms are is they show us regions where we're at constant temperature. But they always fit like a 1 over x type of shape. They're this kind of curve. And so whatever the temperature is at D would definitely not be the same temperature at A. It would be something else. So this is a higher isotherm than the other one. So that just means A is at a higher temperature than D. With that in mind, we know that A has the higher internal energy, and this one has a lower internal energy. So somewhere between A and D, there was a bit of loss of energy of the gas. But if internal energy goes down and that goes up, then it must be the case that a lot of energy flowed out. Now, when you're going from path D to C, there's no work done. Because it's vertical. That's constant volume, so there's no physical change in the piston's position.